Unraveling the mysterious universe and understanding its structure has been an insatiable curiosity of mankind. India has a long history of astronomical scientists. Aryabhatta, who interpreted that the earth rotates about its axis. Brahmagupta, who gave the formula for cyclic quadrilateral, used often in astronomy. And Bhaskara, who determined the parallax in longitude. In the recent times, Subramanian Chandrasekhar, Jayant Narlikar and Meghnad Saha are among a few Indian astrophysicists who took the world by surprise with their cosmic discoveries. Holding the proud legacy, our scientists are an integral part of the world's biggest mega science projects. Mega science projects often involve cross-border cooperation between teams of competent researchers. While the scientific goals of these projects are significant, their worldly benefits are equally important. By collaborating, participating and delivering components for these giant projects, India places itself as a major player in fundamental science globally. In addition, these projects have the potential to create new avenues for science-industry collaborations and to popularize science in the country. Let us analyze India's contribution in various mega science projects. One of the most important mega science projects is CERN, by the European Organization for Nuclear Research. At present, the biggest database collector of the universe, Indian astronomers formed the pillar to its research and development. Established in 1954, CERN is based in the northwest suburb of Geneva on the Franco-Swiss border and is into nuclear research and probing the fundamental structure of the universe. With India becoming an associate member, our League of Indian Scientists has joined the team to interpret the cosmos. With the capability of executing large-scale projects, our scientists are associated with some of the most prestigious projects at CERN. The design of Large Hadron Collider, world's largest and most powerful and largest particle collider, is a handiwork of many Indian scientists, and its construction with infinite precision is being taken care of by scientists and engineers in the Indian industries. Large Hadron Collider smashes groups of protons together at close to speed of light, 40 million times per second, with 7 times the energy of the most powerful accelerators built up till now. One of the 7 important experiments executed by Large Hadron Collider is ALICE. This experiment is optimized to study heavy ion collisions, creating plasma similar to that existing fraction of a second after the Big Bang. Quantum chromodynamics is a theory that describes the properties of the strong interactions between quarks and between protons. It predicts that at sufficiently high energy densities, there will be a phase transition from conventional matter, where quarks are locked inside nuclear particles. Quarks are subatomic particles having electric charge. The reverse of this transition is believed to have taken place when the universe was very young. The hardware for the photon multiplicity detector of ALICE has been entirely designed and fabricated by Indian scientists, from conception to commissioning. In one of the 2 experiments to discover the God particle, Higgs boson, Indian scientists have played a major role in the CMS experiment. Dr. Archana Sharma, better known as CMS Lady worldwide, explains.
We have to look for signatures of particles that existed at the time of the Big Bang but do not exist anymore in nature, like the Higgs boson. So we recreated conditions of the Big Bang, which means we created the available energy so that the Higgs boson could be created, and it will decay immediately because it's not a stable particle.
CMS is a particle detector that is designed to see a wide range of particles and phenomena produced in high energy collisions in the LHC. Like a cylindrical onion, different layers of detectors measure the different particles and use this key data to build up a picture of events at the heart of the collision. This data is used to search for new phenomena that will help to answer fundamental questions like, what is our universe really made of? And what are the forces acting within it? CMS will also measure the properties of previously discovered particles with unprecedented precision. Indian scientists have also contributed substantially to the building and operation of the Large Hadron Collider grid, the global collaboration of more than 170 computing centers in 42 countries, linking up national and international grid infrastructure. The objective of the project is to provide global computing resources to store, distribute and analyze the 50 to 70 petabytes of data expected every year of operations from the Large Hadron Collider at CERN.
My target was to get India involved in the biggest manner possible. We made technology transfer to a company called Micropack in Bangalore. They have made a large number of elements of this detector, and in the future my target is that the complete detector can be made in India. The first station of this detector we are going to install in 2019. The second station will be installed in 2020. And in these 2 years, we will install 144 detectors. In 2022, we will install 288 detector modules. And in 2025, we will install 216 detector modules. So there's a huge amount of work that's happening. And in India, we not only have the technology transfer, but we also have 4 laboratories equipped with all the quality control measurement infrastructure that we have established at CERN that validate these detectors to be certified for installation into CMS.
India as an important contributor to mega science projects is helping greatly in the development of new products, services and new ideas. One such product is the creation of world's biggest ground-based optical and infrared telescope of 30-meter diameter aperture. It is a result of the quest for understanding fundamental issues like the possible existence of life beyond the solar system, the dark energy, believed to be causing expansion of the universe to accelerate, and many other astrophysical phenomena like formation of planetary systems and formation and evolution of stars and galaxies. TMT would enable Indian astronomers to study front-ranking scientific problems such as formation and evolution of stars, planets and galaxies. India has collaborated with the US, China, Canada and Japan to build the TMT at an estimated cost of about $1.47 billion. With this, India is set to contribute in making its very crucial components for the telescope. In fact, many crucial parts of the telescope are already being fabricated at various institutes across the country. Under the joint responsibility of Department of Science and Technology and Department of Atomic Energy, the Indian science sector will benefit both scientifically and technologically. It will bring in the know-how for new and cutting-edge technologies and will make possible gathering information about early stages of evolution of the universe.
The telescope is a 30-meter diameter, and 30-meter diameter is not one single mirror. You cannot make a single mirror of 30 meter. Casting itself is difficult, and then putting there and then moving around the sky is much more difficult because it sags, one single mirror. And also to transporting, you cannot make a 30-meter transporting. So this is now built as a segments. So it has a 492 segments. Each segment is 1.45 meter diameter. And these are going to be aligned, and then they had to make them all act as a single mirror. To make them act as a single mirror, and then you need to have sensors. They sense during the night when you are chasing the stars across the sky, and the telescope has to move from one position to another position. So during that time, things happen. Okay, the gravity changes where they are. Some mirror will be somewhere else, 30 meters away, another mirror is here, and then because of the temperature changes, and the height changes. So there is going to be a change in the position of the mirrors, relative positions, from one mirror to another mirror. So each mirror is going to be attached some 6 sensors. What these sensors do is they sense the relative displacement of these segments. Okay, whether they are how much the displacement is. So that entire sensor thing is India's part.
You can collect more light from these objects, celestial objects, and basically suppose if you want to see the object which we cannot detect with a smaller telescope, so this can be seen with the help of 30-meter aperture. So the sensitivity of the telescope which increases with the diameter, and the image sharpness increases when the aperture increases. So these two together, the sensitivity of the telescope increases a lot.
So once this displacement information is gathered by the sensor, then sent to the actuators, and then the actuators, what they do, they nudge these mirrors. There is some displacement from, nudge that mirror go slightly up or down, something like that. So the entire actuators we are making in India, so those are some 1600 actuators we have to make.
It is also said to give finer details of not so far away objects like undiscovered planets and other objects in the solar system and planets around other stars. 30-meter telescope, being the largest optical and infrared telescope in the northern hemisphere, will enable several discoveries which will surely inspire future generations. The project will also provide state-of-the-art high-end technologies to the country, which would benefit a number of industries and research and development centers of India.
The monolithic mirror, the maximum size in the conventional telescope which is available across the globe is 8-meter class. So the difficulty in making bigger than 8-meter class is making the mirror. So monolithic mirror, anything bigger than 8 meter is difficult. One is that the fabrication facility, and another one is that handling the mirror, supporting the mirror, because when you go for the bigger mirror, so its weight increases, which needs a complex supporting system, and its thermal inertia increases, and various other problems come into the telescope. And the mirrors are going to be fabricated in our optics facility. The facility is coming up in one of our campus. It's called Crest campus of IIA. So the segments are going to be produced there in that facility using a special technique. It's called stress mirror polishing technique, and we are going to put the machineries and the required accessories and the metrology tools in the facility for making the stress mirror polished mirrors.
The design of the project has just been completed and is in its early construction phase and is expected to be operational in early 2020s in Mauna Kea on the island of Hawaii. While India is collaborating with the international scientific fraternity to conquer space, it has always been in the forefront of developing indigenous optical telescopes. Vainubappu telescope, with a 2.34-meter diameter mirror at Kavalur Observatory in Tamil Nadu, was commissioned in early 80s. It could easily resolve a 25 paise coin kept 40 kilometers away. Deep sky observations could be carried out with this telescope. The world-class 3.6-meter Devasthal optical telescope, another feat achieved in this field, was remotely activated jointly by the Prime Minister of India and the Prime Minister of Belgium in 2016. Located at Devasthal near Nainital, it is the largest steerable imaging telescope in Asia, which is a result of scientific collaboration between the team of scientists from Aryabhatta Research Institute of Observational Sciences, Nainital, also known as ARIES, an autonomous institution of DST, and the Belgian scientists.
In 1980, when I joined this observatory, there were plans to have larger telescope, but it was realized that the larger telescope cannot be put here because of expected light pollution. So site survey to find out some good site was carried out in Uttarakhand area, and after long experiments, long observations, the Devasthal site was found suitable for a larger telescope, now where we have a 3.6 meter telescope.
Located at higher altitude in the central Himalayas and away from big cities, Devasthal is best suited for carrying out observations in background condition and to study the regional environment, particularly interactions between the natural and anthropogenic trace species and climate change. The telescope will contribute to the observations for frontline scientific research in astronomy and astrophysics. It features an optical spectrograph, a CCD imager and a near-infrared spectrograph.
With regard to Devasthal, the prevailing wind throughout the year is from southwest, and in about 5 kilometer radius of this site there is no peak higher than this peak, and hence there is no wind sake. So due to this laminar airflow at Devasthal site, we are getting, we measured and we got the seeing of 1 arc second. That is the kind of median seeing we got. And since we have established the telescope that is about 10 meter above the ground level, so the effect of free air seeing is reduced further. So in fact we are able to see the effect of seeing only to the level of 0.3 to 0.4 arc second, not more than that. So as a result, this telescope is capable of giving you images of sub-arc second.
The telescope is also the first of its kind in India that features an active optics system, which compensates for small distortions in the shape of 4.3-ton mirror due to gravity or atmospheric aberrations. The polarization measurements help understand the nature of some of the stellar and extragalactic sources. Light from astronomical objects is in general polarized to some degree, and its measurement gives additional information related to the magnetic field, the distribution of scattering material, and the non-thermal nature of light.
If the light will be polarized in a particular angle, the intensity will be increased. The polarized light comes to you. The source is there. Source is not an instrument. Instrument has just to find it out whether the light coming from the star is a polarized or not. So if the light coming from the particular object or a star is a polarized, then you are able to see what is the source of the polarization in there. If the source of the polarization is, for example, say scattering or say the reflection, so we are able to see that what kind of the sources are there. If it is a scattering, that means some material is in front of that particular star which is scattered and giving the polarized light. That is light vibration along the one direction. Okay, so if you have this, then you are able to study that particular object in more detail.
To achieve a good signal-to-noise ratio, the 3.6-meter Devasthal Optical Telescope also uses polarizing filter. Indian scientists with their knowledge and expertise have been recognized all over the world. It is no surprise that they were equally part of the team that won the Nobel Prize of the Millennium for gravitational waves. It was a direct detection of gravitational waves arriving from the merger of two large black holes in a distant galaxy a billion light years away. Though the Nobel Prize was given to Rainer Weiss, Kip Thorne and Barry Barish, but behind this historic discovery was the dedicated work of 39 Indian scientists from several Indian institutions. The group led by Professor Sanjeev Dhurandhar and Professor Tarun Sauryadeep at Ayuka initiated and did foundational work on developing data analysis techniques to detect the weak signals buried in the detector noise.
The first paper which we wrote in 1991 with Dr. Satya Prakash, was actually gave this, that it was the simplest waveform, just first one term in that post-Newtonian expansion, and we use simple noise and so on, simple noise model and so on. But important thing is that we gave the procedure, how to lay down the procedure, how to go about extracting this particular signal from the noise. And now the procedure which has been used in the discovery is in fact a refinement of this thing.
The group led by Professor Bala Iyer at the Raman Research Institute in collaboration with scientists in France had pioneered the mathematical calculations used to model gravitational wave signals from orbiting black holes and neutron stars.
Current story of gravitational wave detection begins with the discovery of pulsars in 1967. Pulsars are like celestial clocks and allow us to make very accurate measurements of stellar systems. This led in 1974 to the discovery of a system called the binary pulsar. Two neutron stars going around each other, and if Einstein was right, they would emit gravitational waves and eventually sort of coalesce.
Without these valuable contributions, discovering gravitational waves would have been near impossible. Our technical know-how catapults every project and brings it to its trajectory. Taking the same theory of gravitational waves forward, Indian scientists are designing an advanced gravitational wave observatory. This project is a collaborative project between a consortium of Indian research institutions and the LIGO laboratory in the USA, along with its international partners Australia, Germany and the UK. LIGO India bring forth a real possibility for Indian scientists to step forward into the frontier of an emergent area of high visibility to probe the universe.
The site selection was a mammoth effort. It took 5 years. So from 2011 end, we have been looking at sites. We followed about 40 site leads all over India. The main challenge was we needed stable ground in terms of low seismic noise. So you have to go to places which are known to be, stable and the low seismic risk zones. Secondly, we also needed to be away from people, and that's a challenge because we also need people to run such a big facility. So we had to balance between, finding a place which was reasonably big so that people would love to work there. But remote enough that there are no disturbances. We can't have roads within 10 kilometers of the site.
The fact that its location is in India, is its biggest plus points because it's far away from all other detectors. The US detectors are almost from the other side of the earth. So this is almost the biggest baseline that we can get for a network of detectors.
The aim is to set up global advanced LIGO detector network by 2024 that will be operational for 10 years. With zeal, determination and immense opportunities opening for astrophysics both in national and global front, it won't be long when our scientists will dominate the world arena with their hypotheses and discoveries, devising their technological know-how to make our country proud. The various technology transfers in India, driven by innovations from our scientists, also open gates to welcome large foreign investments and large investment flow into the country. With the recent breakthroughs in the astronomical world, India, with its exemplary technical capability, not only takes a leading role in executing large-scale projects, but also goes several notches up globally in terms of research and discoveries. Please mail your feedback on info@vigyanprasar.gov.in. You can also write us on Vigyan Prasar, A50 Institutional Area, Sector 62, Noida, Uttar Pradesh 201309. For more information about our programs, please visit our website www.vigyanprasar.gov.in.